class, and she's going to help you find your number. Now, how many people have not yet registered their iClickers? Very bad. How many people have not yet registered on Blackboard? Very bad. You can't find the class in Blackboard. Search for professor. Do you try option 2? R-U-I-N-A. It's ruin with an A at the end. Okay, any questions about course logistics? Any questions about the website, course logistics? Yes? Can I explain the problem sessions? The problem sessions are going to happen at the same time as labs. So instead of going to a lab once every 3 weeks, you'll go to a lab 2 times in 3 weeks, but you'll go in 2 different places. One place for the physical lab, somewhat analogous to the 2020 lab, and one place for the problem sessions, which will be room 204. And what they will be is 2 hours of solving problems, something like office hours, something like the AEW workshops for mathematics. And the idea is that there's a craft involved in doing problems, and our teaching only by presenting, you watch, is a little bit like the piano lessons I took in elementary school, where there was a teacher in front of the class, and we all watched, and I had a wooden keyboard that didn't make any sounds, and you can't learn to play the piano like that. So the thought is, my intuition, that developing the craft will work better if you have more interaction time, and this is a way of sneaking more interaction time. Something like office hours, something like AEW workshops, something like that. Do you get the idea of it? And so that it's a way of giving you more direct feedback about how to solve problems. Yes?
So will you doing problems that are assigned during the session, or like homework problems, or?
I think, we have to experiment with it. I was thinking it would not be homework problems, and that you would just be developing skills. But we can iterate on that. In the end, my job is to please you, but to please you in deep ways, maybe that I can see better than you can see, like in ways that you'll appreciate in 1, 2, or 5 years. But I'm willing to respond to feedback in terms of your short-term pleasure. Yes? Say again? When will the lab manual be out? As soon as the TAs tell me that they're happy with lab 1, which they haven't done yet. So. Okay, so that means that by Saturday midnight, let's say.
So we will have lab tests next week if they're scheduled on the website?
If the lab is scheduled on the website, you'll have them, and you'll have at least all day Sunday to read the lab manual. Yes? I think we're going to grade the problem session based on attendance and effort. So it's not on quality of work, but on attentiveness. So you can't just show up and be a troublemaker. You have to show up and act all sincere and, what do you call it? Unctuous. What's another big word for it? You get the idea? Any other questions about logistics or comments about logistics? The grading scheme that we're using this semester for the course is a new experiment. I'm always experimenting with grading schemes. My intention is to make the grading as fair as possible, as open as possible, as motivating as possible, some mixture of those things. I like this new formula that I cooked up, but I don't know if you like it or not. If a bunch of you don't like it, we could vote on it and change it.
What did you say the new thing was? I couldn't quite hear you.
Look at the video after class. The videos are posted, and we can do it that way for that question. Okay, let's try out the iClickers. I'm thinking of a letter from A to E, and I would like you to guess that letter. The answer is E. Okay. Very good. Okay. Remember after class to register, to make sure you get your iClicker registered. This last semester is just a pain that people did it later and later and later, and I hope we don't do that again. Okay, so today we're doing 1D motion. I hope I'm going to get through all of these things: a ball and honey, continued, analytic solution, numerical solution. It's a continuation of what you did in recitation yesterday. Talk about potential energy. So we have this idea of this balloon which is going to fall like this, and if somebody has energy, they can give us I don't know, you up for it? We can have our demo. And we would like to figure out what the motion of this thing is when you drop it. So how do we figure that out? We use linear momentum balance. The basic idea in linear momentum balance is that the sum of the forces is equal to the mass times the acceleration. Later in the semester, we're going to be a little more precise about what this means, but for now, there's just a mass and n acceleration. We've got an implied sign convention that everything is positive when it's down like this. And in this problem, we have forces down. We have mg pushing it down. We have minus cv pushing it down, or cv pushing it up if v is positive when it goes down. And this is equal to the mass times the acceleration. Now, there are various ways to manipulate this equation for solving. Right now, what I want to do is I want to manipulate this so it's good for analytic solution. So we can rewrite this equation as v dot plus c over m v equals plus g. Okay, so that's one way of rewriting this equation. So now we'd like to solve this equation, and in general, when we get to this point, we're not going to be able to get analytic solutions, but for some simple problems you can. And this is a simple problem where we can get an analytic solution, and you've been through this whole thing in Math 293, so this is, or 2930, so this is just a review of that. What kind of differential equation is this? Let's just hear words one at a time. Just raise your hand. Yes, what kind is it? It's a first order. You went too far there, but I'll take that. It's a first order, and it's linear. What else can you say about it? Anybody? Not you again. Somebody else? Yes? It's a non-homogeneous or inhomogeneous equation. Homogeneous. And what do we mean by it's inhomogeneous? Is that the right-hand side is not zero. If the right-hand side is zero, you call it homogeneous. How do you know what's on the right or the left? Well, the unknown function and all its derivatives are on the left, and all the known stuff is on the right. And if all the known stuff is zero, you call it homogeneous. What else can you say about this differential equation? Yeah, no. Wait a second. It is ordinary, but I'm not going to. Well, what can I do? You already spilled the beans. Okay, so it's an ordinary differential equation. Okay, now if your name is Neil, you're not allowed to answer the question. Next. Okay, this is an especially simple differential equation because not only is it first order, linear, ordinary, it's a little complicated because it's inhomogeneous, but another simplification, yes, it's a constant coefficient differential equation. So that puts it in the very simple category, but it's a often occurring category. So how are we going to solve this differential equation? We're going to get the general solution, and we're going to say the general solution is a sum of the homogeneous solution, or the general homogeneous solution, plus any particular solution. Any particular solution we add to the general homogeneous solution. So how are we going to figure this out? Well, we're going to first try and find the homogeneous solution. How's that look? We take the homogeneous equation, which is v dot plus c over m v equals 0. That's the homogeneous equation. Next, we get to our solution method. And if you are looking for analytic solutions of differential equations, there is only one solution method. It's not precisely true what I just said, but it's almost precisely true. And the solution method for ordinary differential equations is what? One method. Who said it? Who said guess? Say it with pride. Guess. This is the solution method. So how do you guess the solution is Well, I don't know how the first person did it, but after you've seen it, you remember what kind of guesses to make for what kind of differential equations. Here we make the guess that v of t is, let's say, some constant times e to the lambda t. Now this particular guess is a very famous guess, and for all linear constant coefficient differential equations, no matter whether they're first order, second order, or 39th order, whether they're matrix form or in the long strung out multiple dot form, this is the guess you always make. It's always e to the lambda t. If lambda is complex, that includes sine waves and so on. Okay, that's a check, not a v. In this case, it's a v also, but it's meant to be just a check. That's a very good guess. Okay, so you take that guess and you plug it into this differential equation. Let me call this differential equation 2. Call this 1. This is our original equation. So we take this guess, plug it in, and what do we get? Well, we stick this thing in wherever we see a v. We take derivatives wherever we see derivatives. We carry it out, and we see what we get. So let's start with the second part of this equation. We get c over m times d times e to the lambda t equals 0. And then we have plus, and then we have the first part of the equation. What's the first part of the equation? It's the derivative of that function of time. What's the derivative of e to the lambda t? It's lambda times e to the lambda t. So we get d lambda e to the lambda t. So that's what happens when we plug the guess back into the differential equation. Now what we want to see is it a good guess or not? In other words, is the equation satisfied? The equations are satisfied when the right side equals the left side. We want to make that equation happy. Can we make that equation happy with that guess, or do we have to restrict the guess a little bit? So the guess doesn't tell us what these variables are, these letters or these constants, and we have to see when we plug in the guess, are those constants somehow restricted? Okay, any questions so far? Okay, so what do we see from this? Is one thing is there's e to the lambda t. That thing is never 0, so we can cross it off. Now d might be 0 or not. If it's 0, then we automatically satisfy the differential equation. And what do we have for the solution of d is equal to 0? We have v of t is equal to 0. And whenever you have a linear homogeneous differential equation, 0 is always a solution. And that's so boring that you don't bother to write it. So d equals 0 is boring. D not equal 0, we can cross this off. So we can get, for part of our solution, is that d is equal to anything. So this, if this equation is going to work, it's going to work for any value of d. So there's going to be a solution that's going to be pretty general. We have a whole free parameter in the solution. Now what about lambda? Well, we've crossed off all this stuff here. So we have lambda plus c over m is equal to 0, or lambda is equal to minus c over m. So this is only a good guess if lambda is equal to minus c over m, but it is a good guess if lambda equals minus c over m. So that gives us our homogeneous solution that v homogeneous is equal to d, where d is anything, times e to the minus c over m times t. And another way to write this is as d times e to the minus t over tc, where we define Tc to be the ratio of m to c. So it says it's exponential decay with a characteristic time of Tc, and the characteristic time is proportional to the mass divided by the damping constant. Now, have we got our balloon going yet? So when we take our balloon, we have a mass and we have this damping constant. And what we found out is that this thing accelerates for a while and then it reaches a steady state. There's some amount of time it takes to make that transition from accelerating to reaching the steady state. And what we're saying is that characteristic time is bigger if the mass is big, and it's smaller if the damping is very high. Imagine if this barely damped at all, this thing will just move almost as if there's no friction, and it will take a long time for it to speed up enough to feel the friction. Or if there's no gravity, we still have the same characteristic time in this homogeneous solution. If it starts moving at some speed, it will take a long time to come to a stop, if the mass is big or the damping is small. On the other hand, if the mass is small and the damping is big, like this balloon has a lot of damping and a small mass, it reaches a steady state very quickly. Okay, any questions so far? Okay, so now we've got the homogeneous solution. Now we need to look for a particular solution. And I don't know the language. I don't know either the language for homogeneous or particular. I don't know what those have to do with the English words homogeneous or the English words particular. The particular one, I can make sense of it. I can say, oh, any particular solution, like any old solution. We want to find any old solution to equation 1. So we have this equation 1, v dot plus c over m v equals g. And rather than trying to find a general solution to it, we just want any old solution, any particular solution. Without worrying about it being good for all different initial conditions, we just want any solution whatsoever to that equation. So how could you look for it is you try to simplify your life as much as possible. And you say, what's the simplest possible thing which might be a solution? And again, you make a guess. In this case, the nature of the guess is that you guess that the particular solution looks something like the right-hand side. If you see sine waves on the right-hand side, you guess that the particular solution is a sine wave or a cosine wave. If you see polynomials on the right, you guess polynomials. How about we guess a constant? Let's call that constant C1 and see if that works. Well, you plug it in. So we take this equation, which is our equation 1, and we plug that in, and we get v dot, which is 0. The derivative of the constant is 0. Plus c over m times c1 is equal to g, and this just tells us that c1 is equal to minus g m over c. Did I get that right? Positive. Thanks. Okay, so now we get back to our full solution, the general solution. Our general solution, v of t, is equal to the homogeneous solution plus the particular solution. The homogeneous solution, we said, was any d e to the minus t over tc. And the particular solution we got was gm over c. So this is our general solution. And this is the only way that a balloon can move, whether we start it fast or start it slow. This is what the equations of motion says about how it moves. Now in this particular problem, different use of the word particular, in this example, we know something about how this balloon starts. It starts with 0 speed. So now we plug in the initial conditions. And what do we know for the initial condition? Well, we know that the initial position at time equals 0 is what we'll call 0. It's not really 0. Who knows where the origin of the coordinate system is? Let's just define the starting position to be 0. And the initial speed, well, we do have a sense of what still means. And the initial speed is 0. I dropped it from rest. Now, x doesn't appear in this equation anywhere, so that x initial condition doesn't tell us anything yet. So we want to plug in this initial condition. So we take this solution we have here, we can call this equation 3, and we take equation 3 with the initial condition, and it says that 0 is equal to d times e to the minus t over tc plus gm over c. And this is we're now going to evaluate this at t equals 0. So it says 0 is equal to d plus gm over c, or it says that d is equal to minus gm over c. So what does that tell us? It tells us that the solution of the differential equation is equal to gm over c times the quantity 1 minus e to the minus t over tc. Okay, any questions about that? But let's say we don't just want to know the velocity as a function of time. We also want to know the position as a function of time. So we want to find the position. I don't know how to make a pun out of this, but we always want to find the x position. So there's a joke in there somewhere. I don't know quite how to tell it. Anyway, we want to find the position. How does that work? Well, you say x is equal to, let's see, dx is equal to the integral of v dt. Therefore, we can say x is the integral of v dt. Or if we want to be precise about it, x of t is equal to the integral from 0 up to some time t of v of t prime dt prime. So now we want to plug in what we know for what the velocity is as a function of time. So we get 0 to t. We get our gm over c multiplied by that exponential function, which was 1 minus e to the minus t over tc. And then we have to take this dt, and we have to put primes in both places because the limit of integration here is t, and we can't have the limit of integration, the dummy variable integration, be the same variable. Okay, next we want to do this calculus, and we want to figure out what x is as a function of time. So why don't you do that yourself at home while I do it here in the TV studio, and we'll see if we get the same answer. So just do it yourself, do that integral. Click on E if you haven't finished yet. Click on A when you've got an answer. Ask a question if you have a question about how to do this. Is my vote turned off or something? I was thinking you guys, somebody would have been done after a while. Okay, that's what I want. Okay, so what I got for this was gm over c multiplied by the quantity t plus t sub c multiplied by the quantity e to the minus t over t sub c minus 1, close bracket, close bracket. Okay, now if you agree with that, vote D. If you disagree, vote C. And if you can't tell, vote B. I don't think we want any E's or A's. You either agree, you disagree, or you don't know. Okay, so there's some checks you can make on this, and let's just try some reasonableness checks. One thing is, let's check what is x of 0 equal to. X of 0 is gm over c, so we're going to do checks. X of 0 is gm over c. 0 plus t sub c times, let's see, at 0, e to the 0 is 0, minus 0 is equal to 0. Check. So it gives the right answer at t equals 0. What about units? Let's check the units. So the units of this thing, here we have g. G is a distance divided by a time squared. For example, it's 10 meters per second squared, or 32 feet per second squared. M has units of mass, m. C has units of force per unit velocity. So this one we have to untangle if we want to make sense out of this. So we have distance over time squared up on the top. We have mass. And then on the bottom, we have force divided by velocity. What's force divided? Force is mass times acceleration. So that's mass times distance divided by time squared. Time squared, that's the units of that. And then we have to divide that by velocity, which is distance divided by time. And then we want to see if this whole thing comes out to units of distance. So here we have a distance divided by a distance with a 1 over 1 over distance on the bottom. So we have a distance on there. How about time? We have a time squared on the bottom here and a time squared on the bottom here. Distance per time squared. We have a time on the top here, which gives us a distance times time. And then we have a mass, which cancels the mass, and that's all we have. What was wrong with that? We don't want... What did I leave off here? I did something wrong, right? So there must be a mistake someplace. So I have distance over time squared. I have this thing, I have this thing. Oh, and I have to multiply by a time here. And then there was so that gets multiplied by a time here. That's this time that gets multiplied by this time over here. Then we have time squared on the bottom. That leaves one time on the bottom. That time on the bottom cancels that time on the bottom. Does it all work out to distance or not? It's not much of a units check if we don't check it. Okay, distance works out right. Let's get time to work out. We have 2 times on the bottom, and let's go over here. We have 2 times on the bottom, and we have 2 times on the bottom here. Those 2 cancel. Then we're left over with a time on the top and a 1 over time, which is a time on the bottom, and the time cancels, and it comes out the distance. So the units check. Okay, so it passes some reasonable sanity check. The first one doesn't work. I plugged in. Is that better? 1 minus 1 work better for you? Okay, e to the 0 is 1. 1 is usually 1. 1 minus 1 is 0. Works out. Okay, so there we have our distance versus time. We have our velocity versus time. We have formulas for these things. It was somewhat of a pain in the neck, but this is as easy as it gets. Okay, this is as easy as it gets. It gets more and more complicated when you get to harder and harder problems. Now I want to think about how to do this on the computer. So the computer solution, for the computer solution, we use this other form of the differential equation, which is we write v dot is equal to, and on the right-hand side, we had, it was minus c over m v plus g. So what this is, at any instant in time, we can think of this as known, and this is our crystal ball, which tells us into the future. So we say that the new value, as we move along, is equal to the old value plus v dot times a little bit of time. So we move into the future with this difference equation, which is called Euler's method. But if you like, this is really what differential equations are about. They're about predicting the future from the past. Once you've done it once, you can do it again and again and again. So I would like, with luck, to set this up and show it to you in the front of the room. So I press laptop. Then I plug this in here. And then we spend about 5 minutes pressing buttons and hoping things happen the right way. Laptop. Please control the presentation from the connected device. Do you see anything there? No. Large center screen. Lower. Send to center display. So far, my computer hates this. My computer screen is doing something it's never done before. What? Computer, no input detected. I know my computer's gone haywire anyway. Okay. Let me start with what's going to be on the screen there. Tell me if it acts alive at some point while I'm working over here. So what we'd like to do is set up a MATLAB program to do this. You saw this in recitation. Can you guys, what's your angle over here? I think you can see fine. Right now I'm doing a restart of my computer. It went into a crazy gray world. Are you good?
Sweet. Yeah, I'll work on it. You do that.
Okay. Okay, so how we want to set this up on the computer, and we want to use this idea here. So what we're going to say is, if we knew the velocity at some time, what we'll say is that we're going to get a new value of the velocity, and computers let you use nonsense language like this, where you say v is equal to, and then you can put v is equal to the acceleration times h. And h is going to be my step size. So what I'd like to do is go through a loop where I'm constantly evaluating this expression again and again. And when I go through and evaluate this expression, I've got to have a value for the acceleration. What's the acceleration? Well, we have it over here. It's minus c over m multiplied by v plus g. So if I just do this again and again and again, it will update and it will tell me, if I have a small enough value of h, what's going on. So what I can do then is I can put this in a loop, and the loop can look like this. For I is equal to 1 colon n, and then I just put an end here. I've got my values of v at the end of the whole process. Now in order to get this all to work, at the top I've got to put values for g, let's say 1, and m I've got to put some value 1, and c I've got to put some value, let's say 1 for this. I've got to decide what n is, so let's just say I define h to equal, I've got n to be whatever I want it to be. I'll put my final time to be whatever I want it to be. So here I'll put n is equal to 10, say. I'll put my final time to be whatever I want it to be. Let's say it's 5. And then I'll define h to be equal to the final time divided by n. So now I've got the problem set up so I can do this loop. And I have found now v at the end of this time interval. Now if I also want to know x, I can insert a line here for x. And the line for x is equal to the old value of x plus v times h. Okay, so that is the whole program for calculating what is v at the end of the time interval and what is x at the end of the time interval. Now, which was easier or harder, this one or the analytic solution? Okay, now the analytic solution was as easy as they come. This solution is going to work no matter what I put in here for the acceleration. So no matter how complicated this function is, I type something complicated, the rest of the program stays the same. You got something on the screen behind you.
Yep, I'm opening that lab.
Okay.
The lab. What's the name of the
It's in a folder called 2030 Spring 2011, and it's it opens up. It should open up in some friendly way. I think we want to turn screen sharing on. So.
Yeah, I have to finish starting out first.
Okay, this is very good.
Get there eventually.
Very good. Okay, any questions about this so far? Now, what this is telling us is the value, when I'm all done with this, if I put semicolons at the end of every line here, and I put a semicolon here, and I put a semicolon up here, I get no output. So what happens at the end of this? I have some value of x, I have some value of v, and those are the value of the position and the velocity at the end of that interval of time. Okay, any questions about this? Ask questions about this, because this is the basic thing we're going to be doing basically all semester. Yes?
Do you think there's an eye somewhere in there, like inside the loop?
No.
You know?
No. So the version you saw in recitation yesterday probably had an eye on the inside. And the reason is that in recitation they were more ambitious than I am here, and they wanted to store up all the values of the velocity and the position for all the intermediate times. So they could make a plot, say position versus time and velocity versus time. The way I've done this here, I haven't stored up anything. I've just moved through time, and I've forgotten the past. I've done this like real life, right? You don't know what happened before, you just know the present. And I've just brought us up to date and figured out at the end of the time interval, what are the values of these things. Why did I do that? To make it as simple as possible so you can see the essence of this calculation, which is this line here, which is you update position by looking at velocity, and this line here, which is that you update velocity by looking at the acceleration. That's the whole essence of the integration, numerical integration. Yes? What I've needed to initiate x and v. So I missed the line up here, which was that x is equal to 0 and v equals 0. Very good. Sorry about that. We're getting there?
Yeah, it's got a command. They just run stuff.
No.
There's your editor.
How did you start MATLAB?
I double clicked on it.
I see. Where's the cursor? Is it still with you or is it with me now? Now it's with me.
Yeah, you can see the cursor over here too. There you go.
Now how do I shrink this window?
Hit the green button.
What? Green? I just want to make it smaller.
Yeah. Hit the green button and it'll go back to...
No, I don't want it that size. I want it...
Grab...
I can't grab that corner. I've lost... Oh, okay.
There you go. Does that work?
Now I should have started up automatically. So I want to run this.
Yeah, there you go.
Is it running? It should bring me over to another whole directory. You think it ran? There we are. We're getting good here. Now, where's my 2030 spring 10?
Is that what you're looking for?
Yeah, except for it's got the wrong name.
You all set?
I think so. Getting closer. Okay. Do you need lights low in order to see this? Who would like the lights lower to see this? Raise your hand. Who would not like the lights lower? Okay, some people would. So, how's that? Is that better? Is that better? I don't know what you want. How about that? Okay. So now I have, I would like to think about what I had on the blackboard over there. So we have this demo. If you only look up here to line 13, I have to give you guys lessons about how to talk in class. So if you see somebody talking in class, teach them how to do it properly. Okay, so we only want to look up to line 12 here. We set, let's just say the damping is 1, the characteristic time is 1, g is equal to 1. We have as many points as we want, and so we have the final time is 5. We have h. We can calculate the step size from the final time. So we initialize the v and the x, and we have this loop, which is exactly the loop I put on the blackboard. And then this is the whole calculation. So any questions about this calculation, these lines up here to line 12? And any question should be, imagine that my computer crashes. You can't look anything up. You've got to do it yourself. Is there anything that you're insecure about in terms of doing this yourself? Unless you just totally don't know MATLAB at all, in which case you come to the review session or the beginning session on Saturday. Okay, now we also have the analytic solution, which we can calculate. Somehow I've missed here my m. Do you see m up here anyplace? What happened to m? We need our m. And TC should actually be, TC I should put properly as m divided by c. Okay, now we have the analytic solution, and this is just the formulas that I wrote on the blackboard that we derived. This dot, dot, dot means this extends to the second line. So any questions about writing this analytic solution? Now what we can do is compare the analytic solution to the numerical solution. So analytic solution is one with formulas that has exponentials and so on. The numerical solution, you don't see exponentials, you don't see sine waves, nothing. The computer knows nothing about exponentials and sine waves. It's just adding and subtracting numbers. It's this magic of analytical mathematics that we can write formulas for something which this is really the fundamental idea. If we take the limit as h goes to 0 or as n goes to infinity, this thing defines something, and by some miracle of calculus we can write formulas for it. Unfortunately, that miracle only works for very simple problems. And it only works, I guess this is a pun of sorts, if you're compulsive in a certain way, you want to see solutions like this, but it's a kind of compulsiveness that won't get you very far, because for most problems you can't see this like this. So anyway, now we can look at what we get for x, which is what we get from the numerical solution. Here we have the analytic solution, which we calculate on a computer, but it's still an analytic solution, and we can look at the difference between the two of them. So I want to look at the difference between those two solutions by running this thing. Usually in my life, I don't know about your life, but usually in my life when I run these things, I get an error. So I run this thing. What? I have two TCs. T sub c, TC equals MEC, and where's the other TC? I have this T sub c down here. I don't need this one down here. What? I know I have one, so I don't need it again. So I've got one TC that works for everything. Okay, now I run the code, see if I get an answer. I still get the same answer, or I got actually no answer whatsoever because I had too many semicolons. So now I run it again. I get some answer, and it says something times 10 to the minus 5, some very small number. If I'm doing things right, if I put some small number down here for n, like 5, like only integrate once per second, and do this again, on my Mac I can hit Command Option R, I don't know what it is on your computer, I get this pretty big error. Not that big an error for x. Now how big was x itself? That's an error that comes from what? Run the program again. So it goes about a distance 4, and my analytic solution says 4.0067 or 4 minus 0.0067. Then I can put more and more points in here. I can put 100 here. Let's just look at the error and not bother to look at x itself. Run this again, and I get an error of about 1 over 1,000th. And I can put here 1,000. So I do that arithmetic over there 1,000 times, and I get an error of about 1 over 10,000. And I can do it 10,000 times, and I get an error of about 1 over 100,000. So the error is about a tenth as big as the step size. And now I've got 10,000, 100,000, a million, 10 million. I can do this 10 million times, run it again, and it gives me an error of about 1 part in a billion. Now, you guys grew up in a different era than I grew up, and maybe this doesn't amaze you, but going through, asking the computer to go through that 10 million times seems to me kind of amazing that it just does 10 million times. What about 100 million times? Had to think about it, but it did 100 million times. It just went through this loop 100 million times, did all that arithmetic. Try doing that with Excel or something like that. Okay, any questions about this analytic solution versus the numerical solution, how they are the same, how they're different, how this Euler method works, and so on? Yes? No? Okay, and if you're just puzzled by the MATLAB altogether, then come to the session on Saturday. So I've got 2 minutes left. I'm going to use that to try to just go on just a little bit further. Actually, I'm not going to use my 2 minutes. I'll let Kathy take over. Those of you who have trouble registering your iClicker, Kathy is here to register it for you. So come on up front and see you next time.